In this section, we're going to have a look at confidence intervals in terms of how can we calculate them and what is an appropriate interval to use. I'll start off first of all really talking about why we need them and what they are. So we touched upon this, that if we collect a sample of data and that data is collected from a larger population. So in other words, we've tested 10 users from the total number of users that we might have for an application. We want to use our confidence intervals to let us describe to what extent then that the statistics that we derive from our sample, things like the mean or the standard deviation or things like that, to what extent are we confident that they will be true or reflect a true value for the larger population. And when we're thinking about that as an interval, normally the way we express it then is that we will say, here's our average value, but you should treat this average value within this overall interval. Here's something bigger than it, here's something smaller than it, and we're 95% certain that the true average of the overall population, its parameter, is going to fall inside this interval that we've defined around our mean. So it's just a way then of contextualizing that. When we're talking about or calculating our confidence intervals, you may or you will encounter a couple of different terms. We can either talk about confidence levels, we can also talk about alpha values. When we're talking about confidence levels, what we are meaning is that we are 90% certain that the true population's value is going to fall inside the interval that we defined. When we talk about alpha values, that's that there's 1% or a 5% risk that the true population will fall outside of the interval. So one's just a positive way of looking at it, one's the sort of negative or risk way of looking at it. And depending on the function, some functions you'll put in alpha values, some functions you'll specify a confidence level. How do we calculate then a confidence interval? It's reasonably straightforward, and we're going to take through the steps that we have here. And you can see the actual equation over here on the screen. So a confidence interval is going to be equal to some mean value, and then we will define the interval around this. We'll define an upper bound and a lower bound, so we'll go either up and below the mean, and we're going to define the size of the interval using these three variables. Z is going to be a constant, we'll talk about that. S is going to be our standard deviation that we talked about in the last section, and N is just going to be the number of values that we have inside our sample. So let's look through this. So we're going to start off first of all with the mean value. So that makes sense. So generally speaking, when we have something, we calculate a typical value, or central tendency, or mean value. Along or alongside that, we are adding and subtracting, because the true population value, well, it might be bigger than or mean, it might be less than or mean. So our interval then is going to cover and expand out from our mean. It'll be above it and it'll be below it. So that's why we add and subtract, to reflect the fact that it could be bigger, could be smaller. And the value that we are adding and subtracting is this here, Z times S divided by the square root of N. Z is going to be a constant value. So this is really going to be something that we look up in a table. How it's calculated, we're not really concerned about. We're simply concerned with saying, okay, what is our confidence level or alpha value? And let's go to the table and we'll pick out what this constant value Z is, depending upon the level of confidence that we want to have in it. So if we were saying we want to be 99% certain that the true population's value is going to fall inside our interval that we've defined, we'll look it up on the table, or online calculator really, and we'll get a Z value back of 2.576. If we were only wanting to be 95% confident, we will get a slightly smaller Z value, 1.96. And if we were willing to be 90% confident, we get a smaller again, 1.645. So the more confident we want to be, the bigger the Z value is. And that makes sense because if we want to become more confident in terms of our findings, it means our interval becomes bigger. It gives us more opportunity that will be wrong to capture it inside these values. Whereas the less confident we can be, so we might only be 80% certain it's going to be in this. If we're only worried about 80% certainty, then we can narrow in our guess because we're less certain about it, so we can have a more precise guess. S is going to be the amount of standard deviation that we have in this. And as you can see here, we're plus or minus Z times S. So the larger the amount of standard deviation that we measure, the bigger the confidence interval is going to be. That also makes sense because if we've looked at our data and we know that the standard deviation is quite large, the values are quite spread out. So we've seen from that small sample there can be a lot of spread. And that means then that when we're thinking about our confidence intervals, well, because there's a lot of spread, we need to then make sure our confidence intervals takes it into account. They're going to be bigger as well. Whereas if we've looked at our sample and there's very little spread, all of the values are clustered around this individual one, so standard deviation is small, it means our confidence interval itself also becomes smaller. And the last bit is then when we are dividing by the square root of the number of values. And again, this also makes sense because this will act to make the interval smaller. And the more values we have inside our sample, then the more confident we can become that it is reflective of the true population. So as we sample more values, as our sample size becomes larger, it means then that we can be more certain that what we are measuring, seeing through our mean and our standard deviation, is trying to be truly reflective of the whole population, and it means our intervals can become smaller then as well. So if we think about the equation that we have over there, each of the bits make individual sense. They are things that widen or shrink the interval for good reasons. So here we have just an example of that, and let's have a look at the example first of all. So we've got our 8 users, we've got our respective time on task, we've calculated our variance, we've calculated our standard deviation, we've calculated our mean value. So the mean is our 22.9, the thing we want to build upon. Our standard deviation is 5.5. If we go to our lookup table then, and if we were going for a confidence interval to be 99% certain, then we're going to have an overall value here of 5. So we've got our Z value, we've added that onto the standard deviation divided by the square root of the number of values here, 8, and that's given us a plus or minus 5 if we want to be 99% certain. If we're only concerned about 95% certainty, so the only thing this varies then is the Z variable, it'll become a bit smaller. We plug that in, we get plus or minus 3.8. If we're only concerned about being 90% certain, so we're happy to be a little bit more probability that we could be wrong, we can live with that. Again, our Z value shrinks down. The other variables in terms of the mean, the deviation and the number still remain the same. So all we're doing here is tweaking our Z value. In that sense, it becomes smaller down to 3.2. So overall, what we can say, based on this collection of data, if we were to observe this, that we can be 99% confident that the true mean is 22.9 plus or minus 5. We're 99% certain that the true mean of the overall population is going to be inside that interval. So 22.9 minus 5 to 22.9 plus 5. We are 90% certain, so we're not as certain, that it is within 22.9 plus or minus 3.2. So these are useful techniques then for understanding when we have a value, a mean value that we've observed and a standard deviation that we've calculated, just what sort of ranges the population, the true population parameter may actually fit inside. Now, they are essential. Confidence intervals are essential because most of the cases our sample size is going to be reasonably small. So we absolutely want to understand when we attach a confidence interval to this, just over what range of values the population mean is likely to fall. As we said, we'll use Excel for calculating all of these different values, and Excel has a confidence.norm function, which is the one we want to look at here. It takes in 3 parameters: the alpha value, the standard deviation, and the population size. So alpha was the other thing we talked about here. This is the probability that the chance that we may be wrong. So if we put in a value of 0.05, that is the same as a 95% positive confirmation level. If we put in 0.01, so 1% chance we're wrong, 99% chance that we're right, or if we put in a 0.1, so 10% chance we're wrong, 90% chance that we're right. So we put in the appropriate alpha value, we plug in our standard deviation, we plug in our sample size, and that will then give us the values we see over here in the table, which we can then add and plus to our mean value. When we think then about, okay, so what confidence level should we pick? We've looked at 99, 95, and 90. The reality is you can use an online calculator and calculate this for any value you want of confidence. And you can see over here for some Z values, we've got a range of values shown in this table. So if it's 99, it's 2.576. If we wanted to be 99.9% certain, our Z value becomes bigger, so the intervals widen still. If you're only needing to be 80% certain, so we're willing to take a bit of a gamble just to see where things are, our Z value becomes quite small in that sense. What is the appropriate value? It really depends on what you are measuring. Generally, you probably don't want to drop under 90% or 95%, just depending on what you do. There may be some cases where it is a particularly important aspect that you're measuring. That, for example, if it's number of errors, and it's number of errors in a task that if it is wrong or if an error occurs, there is a significant negative consequence. So there, if you want to be certain about something, that's maybe where you want to go to 99% confidence or beyond that. So always ask, how important is the thing that is being measured? And that will help you determine then how confident you need to be about it. Now, again, if you need to be highly confident, it means that the interval is likely to become bigger, but that simply builds in then the uncertainty that you have around your value. And the fact you're building uncertainty means that you can exercise the appropriate level of caution when considering that value, when thinking about what does it range between. And if the upper range falls into an area that you think is worrisome or is too high, then you know there's a chance that may actually be the case, and it's something you maybe then want to address through your design. Final slide in this here, and we'll finish this section then, is having a look at, in Excel, if we're displaying things as charts, you actually can add in and show the confidence intervals on the bars in the chart. So here's our task completion time, the data we've been using. We're showing here an average value of 22.9, and the little black bar we see on it is our confidence interval, showing the upper and the lower confidence interval. In Excel, it's actually very easy to add this in. Whenever we go to our chart type, we can go down and we can add in error bars. So fair enough, that works for us. We then go to the custom side of this. You can specify a custom error bar. And what you can actually do there is you can drop in a range of cells. So where you have calculated your, for example, 95% confidence intervals, and you've got them calculated in Excel, you can link those cells into the chart and it will display the value in those cells. So it will display your confidence interval. You normally need to specify the positive and the negative side. So in terms of the up and the down, in the data that we're looking at here, they'll be the same. We're not going to have different error bars in terms of the positive or higher and lower aspects of it. So that's all we want to look at in this here. It's easily calculated because we just use the value in Excel, plug it in, get the appropriate Z value, job done. Really important that we do that for the data. Really important that we show that when we're presenting data. Really important that we think about it then in terms of the range of values when we're considering how meaningful our results are. In the next section, we're going to get onto that. We're going to look at about comparing means between two different tests, two different samples. So if I were to run an experiment with two different options and got two different average values, and I wanted to compare the means to work out, is one better or are they in the same error of uncertainty, that's what we'll have a look at in the next talk.